Greetings everyone. We're looking at the residential energy load computation. The original video was made a couple years ago and I was a bit under the weather, but if you can put up with that, the video has a lot of very useful information which will help you complete the assignment. So here we go. This assignment is called Residential Energy Load Computation. It's a very practical engineering exercise. And we're going to take a look at a typical two-story custom home and compute, calculate, estimate the energy load. I've listed some formulas. R value, otherwise known as the thermal resistance. Here's the units. It's got pretty crazy units. You can calculate R total for a wall system by just adding up the R values of the components in the wall, for example. U factor, capital U, is just 1 over R. It's the inverse of R. Here's your main equation, Q, which is the rate of heat loss in BTUs per hour. BTUs are British thermal units. British thermal unit is the amount of energy that it takes to heat 1 pound of water 1 Fahrenheit degree, 1 degree Fahrenheit. That's how it's defined. It's a very common unit in this type of problem. So Q equals UA delta T. That's the basic equation, right here, where U is the inverse of R. So you add up all the R's, you take the inverse of that, and that gives you your U value. A is the area of all the walls in the building. And delta T is the difference in air temperature between the inside and the outside of the structure. So there's a little procedure on how to do that. I'll be going over that in detail. And then there's some instructions. We start with the set of plans for the residence, which is right here. This is posted on the student portal. So this is a pretty typical set of architectural plans. See, these sheets are numbered starting with an A, so this is the architectural set of plans. This is the outline of the new structure. This is the property line out here going around the structure, and here's the street out in front. So this would be the front of the house here. And you can kind of toggle through these. Proposed residence and landscaping plan. And then it gets into the floor plans. So first floor here, second floor here. Just looking at it here. The porch, so I'm guessing this is the front. Yeah, here's the garage over here, so this is the front. So you would walk in the house, there's a great room, a dining room, a living room, the kitchen's back here, laundry room, bedroom on the first floor, and then the rest of the bedrooms, including the master bedroom, are on the second floor. And this just goes through the architectural set of plans. That's a roof plan. This is showing the contractor how to build the structure. A reflected ceiling plan is just a way to show what's on the ceiling, all the lighting, fans, skylights, smoke detectors, that sort of thing. And it's as if there was a mirror on the floor and it's reflecting back at the ceiling. That's why it's called a reflected ceiling plan. All right, now it starts to get interesting. So these are the exterior elevations, east, south, and so on. So you could, if you had to, add up all the square footage of every exterior wall. You could add up the square footage of the roof. And it takes a while, but it can be done from the elevations. You can also add up the square footage of the glass, all the windows. Doing this. Fortunately, this set of plans has that information in the back, and that's where we're headed. A section, anytime an architectural set of plans says sections, it's a cut. It's a sectional. The house was cut down the middle, and this is what you're looking at. It's called a section. Door schedule. Every single door in the building is listed with its dimensions and what it's made out of and so forth. Same thing with windows. Every good set of plans will have a door and window schedule. So you could pull off all your dimensioning information from this if you had to, but fortunately we don't. And it gets into all kinds of details, several pages usually of that. Kitchens, these are called interior elevations down at the bottom here. So this is you standing in front of something looking at it. So this would typically be for the kitchen, bathrooms, cabinetry, laundry rooms, stuff like that, how the bathrooms are laid out. Keep cruising down. Now we're nearing the end of the architectural set. So now we're going to get into the structural set. So things start with an S. So sheet S1, S2, and so forth. So this is the structural engineer's work here, where everything is analyzed from foundation, walls, framing, roof structure, from a structural standpoint, and how it's all framed. Then there's a bunch of details typically dealing with joining and foundation details, pad footings, rebar placement. You can see rebar inside each of these sections. Typically there's a few pages of that. And ME is mechanical electrical. So now we're dealing with electrical, lighting, fans, heating, air conditioning, ventilation. And here is the page we want to look at right here. This is sheet number ME2-1. This is all the Title 24 stuff. Down here it says Title 24 calculations. So these are the energy calculations. And so if you can get a hold of this for the set of plans you're looking at, this will save you a lot of time. Because this person has already calculated, here's the walls, they've already calculated the square footage and area of all the exterior walls, the square footage of the roof structure, of the floor slab, the concrete slab, 2,155 square feet, and of another little raised floor on this house, wood framed with a crawl space underneath, which is just 484 square feet. I don't know where that is on the plans. You would have to go back to the floor plans and figure out where that little piece was. But R13, R30, R19, that refers to the insulation, the fiberglass batt insulation that's inside those wall structures. Then you have the windows here. Windows on a set of plans are known as fenestration, and they're giving you the square footage on each side of the house. So I went ahead and totaled that for you. The total there is 1283 square feet. And as a U factor, for windows, they just give you the U factor, 0.34. So you can use that information to easily compute the energy load requirements for the house. What I did is I did this on a spreadsheet. You can do it by hand, certainly. The advantage in using a spreadsheet, Excel or Google Sheets or one of the other spreadsheet packages, is that once you enter this information, you can easily tweak it and play with it and do a what-if analysis on it and try different scenarios to see what saves you energy and so forth. So when using Excel, you can type words. You know, I'm just assuming maybe you're not an expert with Excel, so I'll go through a few of these details. Right here, you can just, let's say there was nothing there. So just position your cursor there, and you can type just like a word processor. And other cells, you can add numbers. So you just use your number pad and type in 70. And you just go down the line entering values. Then you can drag if you need, if you're typing in phrases and you need the column to be wider, you just grab up here and drag it as wide as you want it. And so I've set up kind of a template here with the different components of the house, walls, windows, roof, and so forth. I'm entering the square footage here, which I will do in a second. Delta T means the difference in temperature between inside and outside. And so I've put a formula up here, you can see up here in this little cell up here the formula that I've put in. So I could just type a 20. I could just position my cursor there and type 20 and hit enter, and it would put a 20 there, which is the difference between the 70 degree inside and the 50 degree outside, and that would suffice. But I wanted to make my spreadsheet a little bit easier to change and modify and play around with, so I put a formula in there instead. And this is the beauty of a spreadsheet. So just position your cursor there, type equals. I'm going to go 70, so just click there, then hit the minus key for subtract, and then click there, so it'll be 70 minus 50, and then hit enter, and it computes 20 for me right in there based on here. So now I could say, oh, what if my outside temperature is only 10 degrees? This is a wonderful day in, I don't know, Montana. Type in 10 up here, and it automatically adjusts all my delta T's down here. And you know, this is the beauty of using a spreadsheet for this. So for delta T, I have formulas in here. You have to be a little careful. You could enter the formula in each one individually, or if you put a little dollar sign, see, I'm doing this up here in this area. If you put $B, $2, $B, $3, now I can take that and just drag it down, and it brings my formula into all four. And you need to put little dollar signs there, so it always does B2 minus B3. And that's the only trick there. When you get to the slab, the concrete slab sitting on the ground, it is concerned, the slab cares what the earth temperature is. What's the temperature of the dirt, in other words? You can pretty much always assume, you know, at the latitude that we're at in North America, the earth is always going to sort of be around 55 degrees Fahrenheit. So I just typed in a 55 there, and for the formula here, I typed in B2 minus B4. So each cell has got a letter and a number. B2 minus B4 will give me a delta T of 15. So in this portion, I'm just entering the R values. Now, I got this and this and this right off the plans. That's given right here. The wall cavities have R13 insulation. The roof cavities have R30. The floor R19. So that means there's about 3 inches worth of insulation in the walls. There's about 8 or 9 inches thick insulation in the roof structure. And there's about 6 or 7 inches thickness in the floor. That's what that basically means. Because fiberglass batt insulation has an R value of about 3, 3.5, 4 per inch. So that's where I got those values, and I can change them if I want to. If I want to see what it does to my costs, I could get rid of the insulation altogether, and I could beef up the insulation and play around with it that way. These other values I'm lumping under other components. And so in the homework instructions here, it tells us that the walls are framed with 2x4 studs. The exterior cladding is wood bevel siding over tar paper over 1/2-inch plywood. See, each one of those has an R value that you look up in this table. For example, 5/8 drywall has an R value of 0.56. And plywood has an R value of 1.25 per inch thickness, and so forth. You can just go right down the line. The tar paper business is right here. It's got a very, very low R value. It's known as roofing paper, building paper. It's an asphalt impregnated paper that serves as an underlayment, and we just usually call it tar paper. That's where these R values are coming from this table. And you could easily look these up online. There are many, many tables like this online. The roof gives you the structure, so you sort of construct the wall. Here's what we're doing. We're taking a wall cavity. It says it's framed with 2x4s. Okay, that means it's 2x4 is actually 3.5 inches wide, going the long way, and that's full of insulation. In the walls, it happens to be R13 insulation. On the inside, you have a layer of drywall. That's the drywall or sheetrock or gypsum board that you see on the inside of your wall. So that's 5/8 gyp board. It's called, a lot of times it's just sheetrock nailed onto the wall. On the outside, you might have a layer of plywood, which I believe is called out as 1/2 inch. So we would say 1/2 inch ply. And you got a thin little layer of tar paper, which serves as a moisture barrier. So we'll call it tar paper, for lack of a better term. And then you have some kind of siding. Might be bricks, might be stucco. In this case, it's a tapered wood siding. Well, each one of these has an R value associated with it that comes from that table that we just looked at. And so the gyp board 5/8 is given in the table at 0.56. So let's add them up here. 0.56. This R value is given. The insulation is R13. 1/2 inch plywood, well, it's 1.25 per inch. So we might have 0.63 for 1/2 inch. Tar paper is really, really small. Our value of, if you want to round it off at 0.1, that would be fine. Wood siding does give you a little bit of insulation, not a lot. I'm trying to find it on my chart here because I don't remember. Look under the siding. Wood bevel siding, 0.8. Not very much at all. Most of the insulation value in the wall is coming from the fiberglass batt insulation. There's no surprise there. Well, you just, R total equals R1 plus R2, ... So you just add them up. There's the insulation, there's the gyp board, there's the plywood, there's the tar paper, and there's the siding. So you could add it up by hand, or you could just do it this way and list them. Just type them into these cells, call it other components, and then sum them down here. See that little sigma right there means sum of the R values. Well, the way you do that in Excel, let me delete that for a second. You come up here and you hit this auto sum, and we don't want to add the delta T, so we just grab it and maybe pull it through like that and hit enter. Okay, and we do that the same for the next one down. Let me delete it here just to demonstrate. Come up here, hit auto sum, and we want to always include those cells. And then you get sick of doing that, so you just grab that and pull that down to the rest of them. So it can be done really quickly. Once you get the top one in, you just pull it and drag it down, and it does the same operation on all of the rows. Okay, so that's the sum of the R values. In the walls, we have a total R value of 15. For the windows, what I did, since the plans give us a U factor for the windows, let me blow this up just a little bit more. 0.34. Windows are always stated as their U factor. No problem, just take the inverse of that. Because here, U equals 1 over R. U factor equals the inverse of the R value. So if the U factor is given at 0.34, well, the R value is 3. It's just the inverse of 0.34. So I plugged a 3 in there. All right, continue on. And the roof has 30 in the insulation, and then several other components in the roof structure, plywood, drywall, that kind of thing, which are given in the problem right here. 3B, roof, concrete floor, wood frame floor, windows. So that's where I'm getting those values. The raised floor is listed there, and the slab. So this totals up the R values for each one. Then this column is just, you see the formula over here, it's just taking 1 over the R value in each case. So in other words, let me clear that and I'll demonstrate. Anytime you want to enter a formula, start out by typing equals, and then type your formula, which would be 1 divided by, and then click on that cell, and then hit enter, and that gives you, and then you don't need to repeat all those keystrokes, you can just drag that down to save time. And you may not want all those decimal points, so come up here and you'll have something like this at the top where you can kind of cut down on the number of decimal points. And then the last column is where you would calculate your heat flow, your heat loss for each of these components, wall, window, roof, and so forth. So that is going to follow the formula Q equals UA delta T. Well, we have the U here, we have the delta T down here, and all we need to do is enter the square footage over here. So for that, we're going to need the plans. The walls have 2939, so come back here and enter 2939. I'm going to change it slightly because I don't want to just give you the answer to the problem outright, but I want to show you how to do it. I'm going to type in 3100. Windows, okay, come down here, I added that up for you, 1283. So I'll type in, I don't know, 1350 or something close. Okay, roof, again, come over here, it's given as 2574. I'll use, I don't know, slightly different number. The raised floor portion, where are the plans? The raised floor is right here, wood frame floor. So 484. I'll use 400. And lastly, the slab, 2155. So I'll type in, I don't know, 2100. So when that's done, the Q's will all calculate. You see what I've done here in terms of the formula for Q. Right here I've got a series of cells. So let me do one of those for you. Let me delete that. You start out again always with equals. And the first term is U, so it would be that. Then you hit times, which in Excel is an asterisk. Then you need the area, so click on that. Then you hit times again, the delta T, which comes from that cell. Then you hit enter, and then to save on keystrokes, you just drag that formula down. And so what it's telling me is that the BTUs per hour in this yellow box from this residence, given an outside temperature of 50, is 93,000 per hour. And to calculate the cost, this is the formula I entered. Let me show you how I did that, so I'll delete that. So the cost per therm I've entered at $1.27. I got that from a recent power bill. So I know it's pretty accurate. A therm is 100,000 BTUs. That's just a term used. 100,000 BTUs. So what you need to do in this formula is go equals BTUs, so click on that, divided by 100,000, divided by 100,000 like that. You need to put a couple of, just hit escape a couple times. What I should have done is gone equals parentheses, open parentheses. That divided by, which is a slash, 100,000. Now close parentheses. Times the price, which is right there. So click on $1.27. And that will give me the cost per hour, dollars per hour, to heat the home under these conditions. So let's take a look at this, analyze this for a minute. Where are we losing most of the heat? You might guess the windows, right? Wrong. The windows, in this example, yes, they're losing 9,000 BTUs per hour, which is a pretty big number. But look at the floor slab, since it's, let's see, concrete is not very insulative. You might be surprised to learn that. Concrete and brick and masonry are pretty good conductors of heat, unfortunately, so they don't serve as very good insulators. Well, we're losing by far the majority of heat out through the floor slab. So we could add carpeting and a pad, you know, and that might contribute an R value of 1, let's say, and that does kick it down quite a bit. See, you can come over here and click in 0 for insulation, and we're losing about 79,000, which is almost the total. If I just add a little bit of insulation in the form of carpeting and a pad on top of the floor slab, we cut that way back. Now it's 48 cents an hour. Or I could actually insulate the slab. Before I pour the slab, I could put down an inch of polystyrene insulation. Think a big sheet of styrofoam, which many people do. That's about 4. That's an R value of about 4 per inch. And that kicks it way, way, way down. And that's pretty easy to do, just adding a little insulation under the slab before the slab is poured. So there are various ways of helping out with the floor slab. Let's put that back to 0 for the time being, just for fun. Let's change the outside temperature to 0 degrees. Let's say this was in a very cold climate. You can see how the cost rises. So $1.66 an hour. You know, if you're heating for 10 hours a day, that's $16 a day. That's almost $500 a month. That's a lot for a heating bill. So in that case, adding a little bit of insulation under the concrete really, really cuts back. That's 76, 10 hours, that's $8 a day. Now we've cut our heating bill in half. So the real usefulness in a spreadsheet is in the fact that you can play with the numbers really, really easily. Now, if we took all the insulation out of the walls, what would happen? We're doing $1.19 an hour down here now. Let's get rid of all the insulation and the walls. Now we went up to $1.90. So we went from $10, $12 a day now to, you know, we went from, I'm sorry, what was it, $1.10 an hour? 11 bucks a day up to $19 a day, which is quite a bit a month, just taking out insulation. Let's see, we had 13 in the walls, we had 30 in the roof structure, and we had 19 under the raised floor, so that puts us back to where we were. So there are many things you can do with a client as you're sitting down in comparing different options. Adding more insulation costs more money initially, but you save a lot on energy. You can explain to your client exactly how much they will save. If you want to attack this problem, probably the floor slab would be the first thing you'd want to do something about. So you could put carpeting in, If the client didn't want to do that, you could put insulation under the slab. So this is a very typical engineering estimate. Using Excel is very important to this kind of work, and of course you could attack this many ways. You know, somebody could say, did you consider the doors? What about the garage door? Did you consider the bodies, the humans, the occupants in the building? They throw off heat. Did you include those BTUs? Well, no, we haven't. What about the convection in the house? What about the wind outside? You didn't include any of those. Well, so there are many ways to attack any engineering estimate. And if the client wanted to pay you thousands of dollars, you could factor in all those things for sure. But if you just want a quick and dirty estimate, it takes maybe an hour or two to put together. This would be one way to do it, and at least your client would have some just rough numbers to go by very quickly to kind of determine what direction to head. So you can do this assignment on Excel, or you can do it by hand. Doesn't matter. Try to do it on a spreadsheet though if you can. If you have any questions about spreadsheets or about the assignment, just let me know.